Here is the lecture for section 7.3 about volumes. In the previous lectures, we had talked about the fact that, you have some expression dx or dt that represents a small little bit of something, a little bit of time, a little bit of x. And when we multiply that little bit of x of width times the height of a rectangle, you get the area of a rectangle. Um, in this section, we're going to say that the integrand, instead of representing a height of a rectangle, it instead represents the cross-sectional area of some sort of solid, some sort of three-dimensional figure. Um, and the uh, multiplication of that cross-sectional area, which we may think of having some unit like square meters, times this dx, which is in meters, gives you something like cubic meters, which is a measurement of volume. We are going to, to arrange our integrals to represent cross-sectional area times a little bit of thickness, getting a little bit of volume in each of those cross sections, and then adding up all of the volumes, the little volumes, to get a total volume. Our first example, we have this pyramid, and the pyramid could be thought of as a bunch of cross sections perpendicular to the x-axis. Um, each of these cross sections are dx thick. And for some arbitrary x, so some arbitrary value down the x-axis, the cross sections end up being squares, with each side being x long. So we can think of the cross-sectional area as being x squared. So therefore, we can think of the volume as x squared times dx. And again, that's a little bit of volume. We would like to add up all those little volumes as x varies from 0 to 3. And there's our expression to represent that volume. If I take the antiderivative of x squared, I get 1/3 x cubed. I'm going to evaluate that from 0 to 3, which means I get 1/3 times 3 cubed minus 1/3 times 0 cubed, or I've got 1/3 times 27, which is 9. And so there's our using calculus to find the volume of that pyramid. You might also recall that the volume of a pyramid ends up being 1/3 base area times height. In this case, the base area is this square down at the bottom, which is 3 by 3, so the base area is 9, and the height was 3 as well. And you can see that also gives us a volume of 9. All right. A really common way of creating a solid is to revolve a region around an axis. So let's say we have this region. It's kind of fish-shaped. It is the region found between the x-axis and the um, curve 2 plus x cosine x. Imagine twirling it, and here's like a 3D representation of that region being twirled. And as it cuts through all that space is considered as part of the solid. We could try to mimic making that kind of drawing by drawing a reflection of that region, and then choosing an arbitrary point, and then making an ellipse, which represents a cross-sectional circle. Now, I drew a little extra on that ellipse to give it a little bit of thickness. Then we can think of that thickness as being the dx, as being how thick a disk made from that circle, and giving a little bit of thickness. What is the cross-sectional area for these? Well, the area of a circle, and each of these cross sections are circles, is pi r squared. In this case, we might highlight the center of rotation, which is an arbitrary x value, comma y, and this coordinate on the curve, which is that same arbitrary x value, and then the value of the y value. the y value on that curve. Well, the distance between those two spots is the radius, or in this case, that distance is 2 plus cosine of x squared. So if that's the cross-section area, then we can say, well, the volume is going to be that cross-sectional area times that thickness, the thing that gives us that third dimension. And in this case, as x varies from -2 to 2. This particular integral uses some techniques that we haven't learned in class, so we're going to evaluate this integral on our calculator. Let me get my calculator ready. Let me go ahead and go into calculator mode, and that integral was from -2 to 2, and the integrand was that cross-sectional area, pi times that representation of r, which is 2 plus cosine of x, and then that whole expression was squared because the r value, 2 plus cosine x, is squared when we find the cross-sectional area of a circle. Let's go ahead, we'll put in x. We get a crazy value out. We probably just want the decimal version of that, 78.213. So we would say that this is equal to 78.213. Now, we are not told of any units here. We're not, this is in inches or meters or centimeters. We're not told. So we'll leave it there. If there was a unit given, we should give a unit back in terms of that volume. The next example is a little trickier. All right. We've got a region. Which is enclosed by the y-axis, the graph of this parabola, and x equals y, and we're in the first quadrant. Let's draw that out. So in fact, I'm going to draw this even bigger. I'm going to use up this whole space so that we can make sure that we see all of it. We've got the y-axis. We've got 2 minus x squared, which means I'm going up here at 2, and I'm going to go down, right? And x equals y, which is coming in through here. So if I wanted to highlight the region that is being twirled, it will be that red region, and we're going to revolve it around the x-axis. Now again, I'll just kind of draw the reflection of that red region to make that green region, and then we'll say, all right, imagine this being the center of rotation for some arbitrary x. That point on the red curve would go and become the point on the green curve. And there is, again, from a corresponding point to a corresponding point. And again, this cross-section has a little bit of thickness, and that thickness is dx. Now, for an arbitrary x, the center of rotation is x comma 0. And this point here is x comma x, and this point here is x comma 2 minus x squared, the y values. Why do I want to do that? Because what we have is a cross-section which looks like a circle with a circle taken out of the middle of it. And we only want the circle that's on the outside. So how do we do that? Well, let's call the inside circle little r. Let's call the radius of the outside circle big R. And we might think of the area of that outside, but not the inside, as pi big R squared minus pi little r squared. Well, if you factor out the pi, you get pi times quantity big R squared minus little r squared. That means our cross-sectional area for this problem is pi. My big R is this distance from the big outside to the center. That distance from the high y value to the low value is 2 minus x squared. It's a little thick. Let's go to a smaller part. 2 minus x squared. And there's my big R squared. My little r is right here. And that, again, the high y value is y, low y value is 0. That's going to be x squared. And so there's my pi big R squared minus little r squared. The thickness of that, now it's not a disk because it has a hole in it. We call it a washer. The thickness of that washer is dx. And we want to do this from the lowest x value, which is at the y-axis, which is 0, to the highest x value. I'm not sure where that high x value is. We'll have to solve for it. Let's set these two curves equal to each other to find that intersection point. 2 minus x squared is equal to x. That means 0 is equal to x squared plus x minus 2. And that factors as x plus 2, x minus 1. Let's see. That means x plus 2 is equal to 0. That means x is equal to negative 2. And I think that would be the spot where these two curves cross down here. And then x minus 1 is equal to 0, or x is equal to 1. And I think that's where we're here. 1 comma something. 1 comma 1, I guess, because it has to meet that one. If I put 1 in here, I get 2 minus 1 squared, which is 1. Yep, 1 comma 1. So the highest x value for this region is 1. And now we've got an integral expression, which indeed represents the volume of that solid. Let's pull that pi out. Let's expand this. We get 4 minus 4x squared plus x to the 4th minus x squared dx. So, as I go from 0 to 1, so pi 0 to 1 of x to the 4th minus 5x squared plus 4 dx. Let's go ahead and take the antiderivative of that. I get 1/5 x to the 5th minus 5/3 x cubed plus 4x is evaluated from 0 to 1. So that's pi times 1/5 1 to the 5th minus 5/3 1 cubed plus 4 times 1 as the high end. And I'm just going to cheat here. I see it's 0 minus 0 plus 0 as I plug in the zeros. Plug in the zeros from that lower bound of integration. So I got pi, looks like it's 1/5 minus 5/3 plus 4, common denominator of 15. So about 3/15 minus 9, nope, minus 25/15 plus 60/15. So it's 63 minus 25, 63 minus 25, 5, 3, that's an 8 and 38. So it looks like I've got 38/15 pi for my volume there. I'm only essentially doing one of each type of these problems, and I'm not even doing all the different things that you might do in terms of what axis you revolve it around and holes and things like that. The only way to get good at these problems is going to be to do a lot of problems. There's certainly a lot of problems in the practice set and lots of videos that I've made if you get stuck. Let's take a look at this last problem. In this last problem, we have a problem that's pretty popular in the AP exam. We have some sort of base, perpendicular to one of the axes. We have cross sections of a particular shape. These are semicircles, right? So you can kind of see for some arbitrary x, you have a semicircle. Now, I typically can't draw these really nifty 3D drawings. I typically say, here's my cross section, and then there is a a semicircle coming out of the paper into the up direction from my paper. But if I take that cross section, I can lay it down onto the paper. And so we kind of see that cross section. Here's my arbitrary x. This is x comma 0. This location right here is x comma 2 sine of x. Let's talk about the area of that cross section. And that is it's a semicircle. So it's 1/2 pi r squared. And our r squared here is tricky. This distance here, not r. That distance there is a diameter, not a radius. Let's cut it in half. So 2 sine x over 2. Those 2's cancel. It looks like we get 1/2 pi sine squared x is our description of the cross-sectional area for some arbitrary x. If we want the volume, we'll want to go and take that cross-sectional area, multiply it by a little bit of thickness, because each of these cross-sections are a little bit thick in the x direction. And we'll do that from the lowest x to the highest x. This particular integral, again, uses a technique that we really haven't talked about in class. So we're going to we'll evaluate this on the calculator. Shift plus. We're going to go from 0 to pi. And our integrand was pi over 2 times sine of x. And we'll square that. And our calculator says that that answer is pi squared over 4. Pi squared over 4.